Let's now go over a sample problem. And this sample problem is basically the following. Here we're given 3 molecules, and for each molecule or ion, we want to determine A, the best Lewis structure, B, we want to determine the electron and molecular geometries, and determine if it's polar or nonpolar overall. Alright then, let's go ahead and do this one. So xenon trioxide. So my central atom is going to be xenon. Okay, I'm going to surround the xenon with the oxygens like that. And I'm going to connect everything to the center like that. I'm then going to proceed and complete everybody's octet. So each oxygen is going to need 3 lone pairs, and the xenon is going to need 1 lone pair itself. All right then, let's go ahead and see if we have used the exact number of valence electrons allotted to us. Okay, 3 oxygens contribute 6 valence electrons, excuse me. So that's 18 from oxygen. Okay, the 1 xenon contributes 8 valence electrons. And so I have a grand total of 26 valence electrons that I can use. And let's go ahead and see if we have used 26. So it's 2, 4, 6, 2, 4, 6, okay, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. So this looks all right. Everybody's octet is complete, and I've used exactly 26 valence electrons. Let's look at the formal charges, though. The formal charge of the xenon is going to be 8 minus 5, which is positive 3. Each oxygen is negative 1. Okay, so remember, formal charges of 0 are best, everybody. And so positive 3 is pretty far from 0. So there is another Lewis structure that we can draw, and it's basically a resonance structure. Remember that xenon is an element in period 3 or higher, so it can actually come up with more than an octet. And it turns out that we can come up with a Lewis structure for xenon trioxide like that. And when I do this, look what happens to all my formal charges. Oxygens are now 0, and xenon has a formal charge of now 0. So that's going to be better than our left Lewis structure, everybody. So our best answer here is going to be that one. Okay, next molecule. Oh, polarity. Okay, so oxygen is more electronegative than xenon. So I got 1 dipole that way, 1 that way, and I got 1 that way. This is a trigonal pyramid geometry with a 109.5 degree bond angle, less than that. So less than 109.5. And so when I think about this 3-dimensionally, these 3 arrows that we've just drawn do not cancel. And so this molecule is expected to be polar, everybody. Okay? The dipole arrows do not cancel. All right. I3 1 minus. This is going to be triiodide. So in this case, it's going to be iodine, iodine, iodine. Let's go ahead and connect everything to the center of a single bond. And let's go ahead and assign lone pairs to complete everybody's octet now. This iodine on the left needs 3. This iodine on the right needs 3. And the iodine in the middle is going to need 2 lone pairs. And again, this is all going to be a -1 anion. Let's go ahead and do the valence electron count. So I have 3 iodines, each contributing 7 valence electrons, giving me a grand total of 21. I have 1 additional valence electron from the -1 charge, which means I can only use a grand total of 22 valence electrons. So that's 11 pair. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, everybody. We're too few now. Okay? Now, we're 2 electrons shy, everybody. So we're not going to try multiple bonding. But remember, iodine is in period 3 or higher, so I can actually have another lone pair on the central atom to have more than 8 electrons. Let's see if the formal charges, though, are happy. This iodine here on the left has a formal charge of 0. This one on the right has a formal charge of 0. And this one in the center has a formal charge of -1, everybody. And does everything add up to the overall charge? The answer is yes. And so this is a valid Lewis structure, everybody. And remember, iodine is somewhat electronegative in Funkel-Brisch, and so it's going to be perfectly defined with a negative formal charge. Okay, so that's the Lewis structure, everybody, for triiodide. What's the geometry then? The geometry, everybody, is what we call linear, and that's going to be a 180-degree bond angle. And so this molecule is going to also be non-polar because this molecule is homonuclear, which means we have no difference in electronegativity among the atoms. Okay then, last example, everybody, is going to be SF5, or sulfur pentafluoride. Okay, central atom in the middle is sulfur. I'm going to surround the center with all fluorines, like that. And I'm going to connect everything to the center using a single bond, like that. Okay, the next step is to complete everybody's octet using lone pair of electrons. Let's go ahead and do that. Okay, and you see sulfur has already an octet. In fact, it has more than an octet, but that's okay because it's in period 3 or higher. So everybody seems to be good to go. Let's go ahead and do a valence electron count. I have 5 sulfurs, each contributing 6 valence electrons, giving me 30. I'm sorry, my apologies. I got 1 sulfur contributing 6 valence electrons, giving me 6, and I have 5 fluorines, each contributing 7 valence electrons, giving me a grand total, everybody, of 35 valence electrons. And so when I add this up, I get a grand total of 41 valence electrons, everybody. Okay, so 41 valence electrons. Let's go ahead and see if this is right or wrong. Okay. So there's a little typo here, everybody. I'm very sorry about that. This shouldn't be SF5. This should be PF5. I'm going to go ahead and change that. My apologies. I'm going to go ahead and make that PF5, everybody. So now it's phosphorus pentafluoride. And so phosphorus is going to be in the middle now. And so I'm going to change sulfur to phosphorus. And phosphorus is going to be in column 5. And that's going to contribute 5 valence electrons. And so my total is going to be 40 valence electrons, everybody. Let's see if we use 40 valence electrons or not, which is 20 pair. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and a grand total of 40 electrons, everybody, or 20 pair. So yes, this is the valid Lewis structure for phosphorus pentafluoride, everyone. Okay, so this was a molecular shape and geometry, everybody, using VSEPR theory. And this molecule is going to be non-polar because everything is canceled with all the dipoles. You can see everything, everyone, is going to be canceled just like that. Okay then, thanks everyone for your attention, and I'll see you next time on Educator.com.